In the previous video, we demonstrated a customized version of the cassette interface that we got up and running. Instead of using the standard serial interface board that's part of the cassette interface, we used an 88-2SIO serial board instead. Now, unfortunately, the UARTs on the 2SIO don't have the same status register format as the serial board that's normally used with a cassette interface. So what that means is that any software that uses the cassette that we want to run, like 8K Basic or the boot process even for 8K Basic, would have to be patched in order to use our 2SIO version. And that's exactly what was covered in the previous video. Now, if you haven't watched that previous video, I'd recommend watching it first. It provides some good background for what we'll talk about today. And I also want you to pay special attention to how quickly and easy it was for us to find where in memory to patch and make those patches. The reason for that is because the Altair has a front panel. Altair and MSI were two of the last machines to have front panels, but the ability to stop a program and see exactly where it's executing in single step where you stopped it, and to be able to watch the front panel lights to get an idea of something that just happened. That was unique to these front panel machines, and they gave you the ability to do something like we did in that last video. If you had a machine with no front panel, just a monitor ROM, you couldn't have done anything like that without a whole lot of searching, maybe written some programs to try to search for key byte sequences or something. But anyway, that's good watching, help you understand this video, and it's interesting to watch how easy that was with the front panel. All right, so in that video, we got 8K Basic booted with our 2SIO cassette. We patched 8K Basic and had the cload, csave commands all working. And it wasn't that hard to patch it, but the thing is, as soon as you turn off the computer, all that patch software is gone. If you wanted to run it again tomorrow, you had to do the patches again. So the obvious question is, what would it take to save the patched version of Basic to cassette and also have that bootable without having to make patches? And that's what this video is about today. And we're going to follow the same thing, the same theme of you're a person back in the day without a lot of resources other than the computer you had. And for example, we're running a fairly basic computer with CPU. We have 16K of RAM in there and our 2SIO board. That's part of our cassette interface. And that's about it. So you don't have a floppy system on here where you could use an assembler editor or run CPM to do development on. Frankly, CPM wasn't out yet. All you had was this minimal computer and 8K Basic. What would it take to write your own tape so that you did not have to patch it every time you booted your customized version? So I've got 8K Basic booted. I've got it patched with our 2SIO cassette routine so that the cload and the csave commands work. And now I'd like to write it out to tape so that I can just boot it without having to patch in the future. How could we possibly do that? Well, the first thing you might wonder is, what is the format of the data on these tapes that Altair distributed software on? There was no documentation released for the general public on this at this early stage of the game, but you can kind of figure out that it's at least a two-stage loader. You've entered a bootstrap loader on the front panel, which turned around and loaded something off of tape briefly, because then we saw the light pattern change. And then whatever we loaded off of tape, then spent the next 4 minutes getting Basic loaded. So the bootstrap loader is very short. We can disassemble that by hand and get a clue about what's going on. And if you do that, you can see that the bootstrap loader loads the checksum loader off of tape. We know it's called the checksum loader because it calls it that in the Altair manual, the Altair Basic manual. That checksum loader has to be about hex C2 bytes, about 200 bytes long. We can tell that from the checksum loader. And it's loaded in reverse order, so the bytes are all in reverse order. And it's loaded up at 1F00, which is above Basic, just below the 8K boundary. So Basic itself is a little bit less than 8K total storage. But that's about all we can tell easily. We don't know how that checksum loader works. It would be hard for us to disassemble it. It's 200 bytes. That's a little more than we can really do easily by hand. But in order to make the boot process work with our 2SIO cassette, we would have to reverse engineer that enough to patch it in order to use our 2SIO instead of the normal cassette. And then we'd have to figure out what the format of the data is on the tape that the checksum loader is reading, because we'd have to patch Basic on there to include our cload updates. So my gut feel is undoing and disassembling and figuring all that out back in the day the person owning this equipment without anything but 8K basic, I would say that's beyond their ability. So then the next question is, how else can I write a tape? Well, right now we're up and running. Everything in memory is an image that could be written out to tape, and if we just loaded it back in, it should just run just like we are. Now we're already past the startup dialog where it sized memory and asked if we wanted sine, cosine, all that. So if we just reload what's in memory now, we're not going to get that startup dialog again. But this is for my machine, and it's going to be the same all the time until maybe I add more memory in the future or something, and I can replicate the process I'm about to do. But what I can do with BASIC is write an image of memory out to tape. And once that's out to tape, I could then write a very simple bootstrap loader that literally read all of BASIC in from the tape instead of just trying to read a checksum loader. So let's go ahead and try that process and see what that would be like. So I'm going to write a little program to write out this entire tape. The manual for 8K Basic does tell you how to do I/O to that tape, and it's pretty simple. So right now I've got nothing in memory. We're going to write a program that's going to loop through all of memory and write it out. First thing we need to do is figure out how much to write out. So I'll print how much free memory we have. Let me try that again. Always hard typing around the tripod. It's my excuse every time. All right, so we have 9,860 bytes free. We have 16K, let's see, print 16K, total bytes of memory minus 9860. And one more time, 16 times 10, 24. You know what? I know what the answer is, minus 9860. So 6,524 bytes is about how much we need to write for BASIC. So let's do that. We'll say for I equals 0 to 6523 to write out all those bytes. And there's an instruction for doing I/O to I/O devices in BASIC called wait. And you give it a port number. 18 is the status register for the second port on the 2SIO that we're using for cassette. Remember, that's 22 octal like we've seen in the last video. So this is going to input from octal port 22, which again is the status register. It's going to AND it with 2, which is the status bit in the 6850 UART status register that indicates it's ready to transmit. And it's going to wait until status bit 2 goes true. If it ANDs it with the value 2, as soon as that is true, meaning it's okay to transmit, then it will release control. All right, so at that point, then we want to write whatever's at the memory location indexed by I out to the tape. So we're going to do an out. This just does an out instruction as if it was coming from the processor. Port 19. 19 is octal 23, which is our data port for the cassette on 2SIO. And the data we want to write is what we find in memory. So we'll peek at address I. So this is going to wait till it's ready to transmit, and then it's going to output whatever is at address I. And then we just do the next I. I is implicit here, and it actually runs faster if you don't give a variable name there. All right, so that should write the whole thing out. So let me zoom back here a bit. I'm going to start this tape recording. Let it record a few seconds of leader on it. Idle tone, okay. I'm going to run the program now. And we'll let it go. This is 300 baud. It's going to take a while to write it all out. So when this is all done, I'll come back and we'll stop that tape and take it on to the next step and see if we can figure out how to load it. All right, so saving of that 8K image from memory out to the tape is complete. That image includes 8K basic patch to use R2SIO for cassette load and cassette save. And now we just need to write a loader that I can toggle in on the front panel to read that tape back into memory whenever we want. Now back in these early days, before you had an assembler or editor or development system, you would have had to write this loader by hand. But it's going to be a very short loader, much like the bootstrap loaders in the manual for BASIC. So to do that, you would have written it out on a piece of paper using 8080 mnemonics, and then just turn around and hand assembled it. Now I've taken the liberty of using an assembler so that we can see this clearly. You don't have to look at my handwriting. So here's the loader I wrote. Basically I have some equates that are the address of the ports. That's 12 and 13 hex, which is the 22 and 23 in octal. We're loading this up at 2000 hex, which is up above basic. So this will be above basic, and then basic will get loaded up underneath it. And just like the bootstrap loader, we reset the 2SIO port. And then we're loading H, which is our index pointer, our memory pointer, with 0. We're going to just start at 0. And every time we store a byte, that's this move A into M and increment X, we're just going to increment that pointer and go back into the loop. So here we wait for a byte, we get the byte in, store it in memory, increment the pointer, go back to the loop. So you can see there's no exit for this. This just goes forever. So I will just stop it when the tape counter gets to where I saw it end while I was saving it out. So this is quite short. This is only 18 hex bytes. This is actually shorter than the bootstrap loader for the 2SIO that we entered from the manual. So pretty simple to do. All right, so I'm going to do a video cut, and I'm going to go enter this into the computer, and then we'll turn around and see if it can boot BASIC. All right, so I've toggled that loader in through the front panel. Again, it starts here at hex 2000. That's the start of the second 8K of RAM. BASIC itself will be loaded down into the first 8K. So these don't overlap each other. At this point, all we need to do is release the tape, hit run on the program, and it should start loading the tape. Again, this tape is just a binary dump of memory from when we were last running our fully patched system. So when this comes back up, we should be able to just jump to 0, which is the warm start entry for BASIC, and be right where we left off. So we'll check on this in a few minutes and see how it works. All right, so that load process has completed. I reset the computer, jumped to address 0, which is the warm start address for BASIC, hit run, and nothing happened. So I repeated the whole process again, jumped to 0, again, nothing happened. So unfortunately, it didn't work. I'm not sure why, so that's what I need to dig into. So what I've done is reload 8K BASIC, just like we did in the previous videos where I patched the checksum loader on the fly. Have 8K BASIC up and running. I'm going to use it to write a utility to do a sanity check on this tape to see if it was written right and if I'm able to read it in the manner I expect. So this is the program right here. What we're going to do, I have an array called tape that's 2K elements long. We're going to read 2K bytes off of this tape. Here you can see the for loop that's reading it. Again, we're doing the wait instruction that we saw for the output, but instead of ending with a 2 to check for the transmit ready bit, I'm ending with a 1 to check for read data available. As soon as it is, it then executes this instruction, which does an input from the data register of the UART into the element of the tape array that matches the memory location. After that, then I'll go through a loop looking for how many mismatches I have. Okay, a couple things. Right here, I'm doing an out 3 and an out 18. That's reinitializing or resetting the UART to clear up any garbage that might be in there so it starts off clean. The other thing you'll notice is that I'm not checking all 2048 bytes. I'm checking just the last 1K of the bytes. And that's because obviously BASIC is going to have a large number of data structures and variables, and those might not be the same between what was in memory now and what it was when I actually wrote this tape out. And so rather than include those, I'm trying to jump into where I think there'll be code. The code should be relatively static. And if those all match, then I have a feel that this is probably written right and it's probably working. All right, so let's go ahead and run this program. Let me get the tape running. There it's going, and run this. All right, this only takes about 70 seconds or so, about 2 minutes. So when this is done, I'll come back and we'll look at the results and then figure out what we're going to do. All right, so this has completed. Turn off the tape, and it found 0 mismatch locations. So in the last 1K of that, every single byte matched. So odds are that tape was written correctly and we're reading it correctly, just like we expect. Does this mean there couldn't have been 1 or 2 bytes that were read wrong and caused it not to run? Of course not. That's still possible. I didn't validate every byte. However, I've been using this tape for quite a while where I was hand patching it like in the previous videos, and it's been very reliable. I've had basically no read errors. Not that it's impossible not to have any, but that's not what I'd suspect first if I have 1,000 cases of bytes here that all happen to match. So I'm not going to jump down that path first. Instead, there's got to be something else. And the question is, what could that be? This thing was running just fine and I took a memory image of what was running just fine and wrote it out to tape. And now I put that exact same image back into memory, and it doesn't work. What could be different? What could be wrong? Well, the only thing I can think of, since the memory is all identical, is that the registers aren't the same as they were before. Now, I'm jumping to the warm start entry point of BASIC. You really wouldn't think it would care about registers. You'd probably think it's kind of starting all over. It's not cold start, but warm start's pretty close to starting from the beginning. The only thing I can think of is maybe the stack pointer is used before it finally reinitializes everything. And I'm coming in here on that loader I entered on the front panel, having never set the stack pointer since I turned on the machine. So it's probably pointing somewhere where there's no RAM. I only have 16K in here, so odds are it's pointing somewhere other than that. So what I'm going to do is update that checksum, I'm going to update that loader that we saw earlier, and I'm going to load the stack pointer with a value. The question is, what value do I put in there? For now, I'm just going to put the very top of this 16K board. So I'll put in hex 4000, which will grow down from the very top spot on that 16K board. And we'll see if that will get us up and running. So what I'm going to do is add those 3 bytes into that loader to load the stack pointer with 4000 hex, and then put it in here on the front and then let it run and see if that fixes it. But I'll use the same tape, just have a stack pointer before it goes into BASIC. All right, this is getting close to finishing. You can still see that we're in our loader. The 2000 light is on, and the rest of the program is down here. It's just a short program at 2000 running through just a few bytes above that. These 2 lights are on because that is the I/O address of the serial port. Address is 12 hex that we got up here in the upper 8 bits. That tape counter has to get to 95. It looks like we're there, so that should be done. So now I should be able to hit reset and begin running from 0, which is where BASIC warm start is, and hopefully we get an OK over on the terminal from that. Let's see if we can get both of these in view. All right, cross your fingers. Let's see, reset. All right, there we go. You can see the light pattern change. We're running in BASIC, and we're up and running from where we left off last time. Okay, now, when that tape was written, the program that wrote the tape was in memory. So if I do a list, we'll probably still see that. There it is. So that was actually the program that was in memory writing itself out. So it's there as you'd expect. So to start your day, you just do that, and now you're ready to go. And let's just make sure the environment seems good. Let's see. Oh, I can never type on these. All right, so we're up and running. So that does it. It just needed a stack pointer, and then once it got far enough into the warm start, it seems like it was happy and reinitialized everything. We obviously loaded the exact same data we saved. That program was still in there. So now I can, as a user back in the early days, enter a loader on the front panel that's actually 1 byte shorter than the loader was for the 2SIO. Load BASIC, and it actually loads almost a minute faster, 45, 50 seconds faster, because it doesn't have the leader bytes, it doesn't have the checksum loader to load, and then it doesn't have the overhead, although it's pretty minor, the overhead of the checksum, the data, which has a checksum per 256 bytes or so. But anyway, so this works really good. The only thing is that it won't spit out an error if it gets on while it's loading. Although in general, I've really never had any load errors when I was doing it normally. Doesn't mean it can't happen, but it's a fairly reliable system. But this would definitely have been a way that somebody back in the day could have gotten around not having a real cassette interface had he made his own. And now you don't have to patch anything on the fly. All right, now obviously in today's world, we've had people that have documented exactly what the tape format is on the Altair tapes. They have disassembled the checksum loader, all nice source format with comments, so it's easy to go in and find out how to change that source file and make a checksum loader that would handle the second port on a 2SIO, so that you could put that as part of the checksum loader. People have also written utilities that will combine any program you want, like BASIC, a checksum loader that you make if you want it different, and create a whole boot tape ready to just boot. And so I have used those utilities, those run under CPM for example, to create versions of 8K BASIC and Extended BASIC and the assembler editor package, all ready with all these patches in it to work off the 2SIO. It was technically done with vintage tools, but it was after the point people had assemblers, editors, and disk drives like the CP/M environment and could do things at the source level. So when you find those in the links on the previous video, and I'll put links to those files in this video as well, those were done under CP/M with some tools that other hobbyists had done. I made the patches, but the other hobbyists did all the work in figuring out how those tapes work and how to write them. All right, well, that does it for this video. It's always fun digging back into what it was like in the day. And next, we'll see if we can find some other or more interesting tasks to put ourselves to.